So again, just a reminder to you guys, I don't care if you copy one problem from the internet or the entire document from the internet. To me, copying is copying. So let's look at pressure conversions. So I like to be very sneaky on tests. You should always, and I hint this out, it's very important in this class, you pay attention to units. That's why I say when you're doing your work, cross out the units and make sure the answer actually works. So, you know that 1 atmosphere is equal to 101.325 kilopascal, which is equal to 101,325 pascals, which is equal to 760 millimeters of mercury, which is equal to 76 centimeters of mercury, which is equal to 29.9 inches of mercury. And going to give 2 other conversions. So this is all standard pressure units. So standard pressure. Trying to look up a few more. In this class, we will roughly be treating also 1 torr we'll treat it the same as 1 millimeter of mercury. If you want to be precise, you don't have to write this down. I'll use approximately. 1 torr is really equal to 0.999998575333699 millimeters of mercury. So unless you're writing an answer that includes 1, 2, 3, 4, 5, 6, 7 significant figures, it's close enough to 1 to count. So you can ignore the fact that torr is approximate. We will treat 1 torr, and let me actually, 1 torr is about the same as 1 millimeter of mercury. This is exact. 1 bar is equal to 100 kilopascal. So this is exact. 1 atmosphere is also equal to 101.325 kilopascal. And this is exact. So this is an approximation. Where's another one? PSI. So 1 PSI is approximately equal to 6.894757 kilopascal. I'll add it up here to standard pressure. It's 14.7, right? Yeah, 14.7 psi. One psi. So this is pounds per. So pound force per square inches. This is what psi stands for. So unit conversions. Let's say that I wanted to derive this. What is a pound per square inch? So let's say I wanted to figure out how many pounds per square inch are atmospheric pressure. And all I knew is that 1 atmospheric pressure is equal to 101. No, I won't go there. Never mind. I'm getting too advanced. Y'all don't really need to know that. So these are various ones. The only ones you really need to know is once we start is these 3. You also should know that torr and millimeter mercury are the same thing, so know this relationship. But these values are used enough that you should be able to just look at a problem and know what atmospheric pressure is. So, everyone good? So if if a problem says there are 500 torr, I keep wanting to put 2 O's and not 2 R's, of pressure in a bottle. How many atmospheres of pressure is there? So if you need to convert, you should instantly realize that 500 torr is the same as 500 millimeters mercury. And a relationship is 1 atmosphere is equal to 101.325 kilopascal, which is equal to 760 millimeters mercury. So in order to convert into atmospheres, we just do dimensional analysis. So we plug in millimeters mercury on bottom, with atmospheres on top, because these are all 3 equal. That cancels out. and you would get 0.6578947 atmospheres. If I instead ask what is the pressure of 500 torr in kilopascals, by the way, when you see kPa, you should immediately read it as kilopascals. Usually, if you say kPa to me, I usually don't know what kPa is, because that's not how you correctly say this. You should be calling it kilopascals. Likewise, you shouldn't be calling this ATM. If you say ATM to me, I'm thinking of the grocery store thing that gives money. This is atmospheres. Likewise, if you see an M, or if you see a CM, and you say they're CM, I usually don't think CM. It's centimeters. You should know how to say this in words. So again, as you can also just remember that this conversion factor, you can replace the millimeters mercury with just torr. So we begin with 500 torr, and we're going to plug this portion into it. So here, torr cancels out, and we're left with kilopascals. And that gives us 66.66118 and kilopascals. Let me pull up the test. I'm supposed to give the test on Friday. Come on. Let's see. I think I might hold off. So is everyone good with unit conversions between pressures? These are the main three, and knowing that torr is also millimeters of mercury. Oh, I was nice. This test is multiple guess. Let's see, there's not, it's only going to be, okay, I do give you the 3 R values and this. So you don't have to memorize this for the first test. These 3 values are given, and the R values are given. No, that's all multiple guess except for the bonus. I do not do any kinetic energy problems. I do not do anything with a fusion or Graham's law. It is ideal gas law and combined gas law. And you have to know what Boyle's law, Charles's law, Gay-Lussac's law. And currently there is a way to freely cheat on the test that I allow. I have a note at the top of the test. Change this test as they can cheat. Question mark, question mark, question mark. So I will look in changing the test. So it's really weird. The extremely smart students end up not cheating by doing it. But the students that really paid attention during class came up with a way of cheating that was completely allowed because you don't have to show your work. Yeah, it's a big brain move. There is a big brain move on the test where you can identify no. It's just that my answer choices are not good. Like for example, my answer choices are like 1, 2, 3, and 11,325. And you look at it and you're like, it can't be less than 10. These numbers can't possibly be less than 10. It has to be this one. It's a big brain move like that. I am probably going to change the test if I find time, so that you can't do that. Because the purpose of the test is to test your ability of solving gas law equations. It's not supposed to be your ability to just look at the answer choices and eliminate all but one. Well, I try to make it so that 2 answer choices are obviously can be removed. I like to try to keep at least 2 of them where it's a 50-50 yes. Oh yeah, we don't have any significant figures. This test does have significant figures on it, but all the answer choices are different. So, like for example, if the correct answer was 1,234, the correct answer choice is going to be listed as 1,200 because I rounded it on the test to 2 significant figures. So I do that also, especially for this class, because one, we're supposed to be using significant figures the entire year, but I don't like them, so I have y'all stop doing it. But also it means that if you get something in the calculator, it's really hard to compare. Just kind of rounds to that, but is this the right answer? Like for example, if the answer is supposed to be 1, 2, 3, 4, and on the test it's 1,200. Like 1,200 because I rounded it to significant figures, and you get in the calculator 1220, obviously wrong. You're like, I don't think I did this right, but there's a possible answer choice on it. Or if you typed it in wrong 1 digit and you see 1260, and one of the answer choices is 1,300, you don't know if you did it right or wrong. Right now, I'm probably going to do the test on Friday. I don't know. The only option, if I don't know on Friday, I'd have to do it on Tuesday. Yeah, that's the reason why I want to rush. I'd like to have all your papers graded and turned back to y'all, but not everyone turned it in. So I want to go over Graham's law too. So Graham, let's see if I'm spelling it correctly. Nope. Graham's law is rate A or rate B is equal to the square root of molar mass. And I'm just leaving the molar out for now. Of B square root of mass A. I'm not going to grade it because I told y'all can directly plug time into here. But technically time as a rate is the inverse of time. So you complete one action in 77 seconds. So when you plug it in as a rate, so you should plug it in as, so if you plug in time into this rate, it should be 1 divided by time A divided by 1 divided by time B. So if you divide by a fraction, so let's pull this out. So if you take this 1 divided by time, 1 divided by time A, and if you divide it by a fraction, that's the same thing as multiplying by the reciprocal of that fraction. And thus it should be time B divided by time A is equal to the square root of mass B divided by the square root of mass A. So if you plugged it in directly into the homework problem, you probably got an answer of somewhere a little over 108. Yes. The correct answer, if you actually do the inverse of this and do use it using this, the correct answer should be around 50 to 60 seconds. Again, I'm going to ignore that because I told y'all wrong. Yeah, it's just because when you plug in a rate, so what is a rate? Like this, a velocity or speed is a speed. So that is in miles per hour. Your time unit is in a denominator. So when you have a rate, you're doing something per time unit. So when you plug in a time as a rate, you need to plug it in as an inverse. So your time unit should be in inverse seconds, not seconds. So 1 divided by a second when you plug in time as a rate. But again, I didn't explain this. It's something that I don't have any notes for that. It's just something that I have to look at and go, oh yeah, I need to explain time to them. And I just forgot to do that, so I'm not going to grade number 11. And besides, we don't use Graham's law. It's just introduced with the gas laws. We won't ever use it again. I think partial pressure is going to be used. So let me do an example like that. So suppose we had a container. So let's make this let me drop there. We have a 2-liter Coke bottle. inside of it, we have 5 grams of O2. And we have another Coke bottle. So it's also 2 liters. Inside of it, we got 15 grams of nitrogen. All the temperatures. So this Coke is at 70 degrees. So let's make that 20 degrees Celsius. I think it's 77 degrees Fahrenheit. This is at 20 degrees Celsius. And let's add these gases to a slightly bigger 3-liter container, also at 20 degrees Celsius. Did it give you pressure also? Let's assume that this is at 1 atmosphere. This is at 1 atmosphere. So it gives you temperature, volume, pressure. Oh, what it doesn't give you is the grams. Sorry, I was trying to match this. I was trying to match the question. So it only gives you volume, pressure, and temperature. So we have a 2-liter bottle at atmospheric pressure, only containing oxygen. Another 2-liter bottle at atmospheric pressure, containing only nitrogen. They're both kept at 20 degrees Celsius, and they're transferred to a slightly bigger container and pumped together, while the temperature remains constant. So it's at 20 degrees Celsius. Again, I like to give problems that make you think. So we know that they exist in this container. The question is, how much oxygen do we have? So how much oxygen do we have? How much nitrogen do we have? How much nitrogen, oxygen will go into this container? So to do this, we do ideal gas law. To find out how much, so to answer a how much question, we need to get moles, or grams. So number of moles is equal to pressure times volume divided by the R constant times temperature. So for oxygen, the pressure was 1 atmosphere, the volume was 2 liters, the R constant 0.0821 liter atmosphere per mole Kelvin, and the temperature is 293.15 Kelvin. Atmospheres cancel out, liters cancel out, Kelvin cancel out, and we're left with just moles. So that'd be 1 times 2 divided by 0.0821 times 213.15. And that equals 0.0830992 moles. So this is how many moles of O2 we have. how much nitrogen do we have? So again, number of moles is equal to pressure times volume divided by RT. I should have chose different containers. This is going to come out to be the exact same. So 1 atmosphere for this container. 2 liters. I should have done different pressures because the values are going to come out differently. Let's make this 1.5 liter. So a smaller container of nitrogen. So this container is 1.5 liters, this one's 2 liters, and we're putting it in a 3 liter. So atmospheres cancel out, liters cancel out, Kelvin cancel out, and left with moles. And so we get 0.062324 mole of nitrogen. Now, what I would do is I would use Dalton's law and find out what the pressure of oxygen is and what the pressure of nitrogen is and combine them. So I would say, what pressure would just the oxygen exert in new container? So pressure is equal to nRT divided by volume. And this is for the new container. So volume is 3 liters. Temperature is 293.15 Kelvin. And so this is equal to 0.08 you could do it this way. Yeah. This is mole times 0.0821 liter atmosphere. So you can figure out the individual pressures, or you can just add the number of moles together. It should be taught, or this is the official way of doing it. And we divide by volume of 3 liters. And you get a pressure of 0.6 carried atmospheres. Then we can do the same thing for nitrogen. Oh my goodness, my calculator just died finally. Those are so many years. So now doing it for nitrogen. Pressure equals nRT divided by volume. And that would equal 0.481 mole. No, it's not. It would equal 0.0623244 mole times 0.0821 liter atmosphere by a mole. Divide by 3. And now we get the 0.499998881. And this would be in atmospheres. And from Dalton's law states we can add the pressure, total pressure is equal to the pressure caused by nitrogen or oxygen plus the pressure caused by nitrogen. So we add these two values together. And we get an answer of 1.1 atmospheres. Another thing you could have done is recognize that do this. So if we recognize that Dalton's law states that pressure total equals the pressure of O2 plus the pressure of nitrogen. So pressure of oxygen 2 is equal to the number of moles of oxygen 2 times this R value times the temperature divided by volume plus pressure of N2, which is number of moles of N2 times R times T divided by volume. Since it's the same volume, same T, same R, we can factor. And thus, the number of moles plus the number of moles of N2 times R times T divided by volume. So basically, you could have just added up these two values first and plugged it in for N and got the same result. That makes sense? So either apply ideal gas law 3 times or 5 times. Or 4 times. Here's the code word for the day. There was a code word. Now I have the PowerPoint selected. I wanted to also, before the test, go over the difference between ideal and real gas. I might do that briefly tomorrow. I'm thinking I will have a test on Friday. No, because it was just a test. So besides the problems relating fusion, Besides the problems dealing with a fusion and kinetic energy, does at least the combined gas law and ideal gas law make sense to you guys? Were you having any trouble with it? I think that's going to be it for today. Let me reconfirm. Yeah, everything on the test is Boyle's law, STP. You do have to memorize STP. How to convert. So you do have to memorize 273.15. Oh yeah. So in this class, there's going to be so many constants y'all memorize. I don't memorize any of the gas constants. No, I give you the gas constants on the test. Gas constants are going to be on the test. I don't memorize them because in this class they are too imprecise, and I just use the imprecise ones. And they don't really have a good cutoff point. Like Avogadro's number 6.022. I think the next term is like another 0 and a 1. So it's like even if I memorize the 0, 1 after it, it's approximately just still 6.022. For the gas laws, they're like there's not a good stopping point. You have to memorize like 6 or 7 digits. Oh yeah. I tell y'all need to use 6.022. I forgot to tell. That's another very good point. So again, on the homework and everything, the main constants use the values I give you. 6.022 and 273.15. And yeah, ignore rounding the whole number. Yeah, ignore rounding the whole numbers. I want 4 or 5 digits on every answer from now on. And use the constants I give you. The main reason for that is one, it's good science. You're more precise. The second reason is there is no reason why I should see an answer that's copied from the internet. If your numbers use scientific notation, that's it for the day. See ya.